Okay, you guys, so let's continue on with chapter 9.3, separable differential equations. So just so you guys know, I made a mistake. I forgot to write the 2 right here in the previous problem that I had finished the last video with. So I just fixed it. The correct answer is now listed. So I did that fix for you guys in green right there, okay? So let's start with 9.3 continued. So we're gonna move forward. So the next problem we're gonna look at is y prime is equal to x e to the x cosine squared y, and this time I'm going to give you an initial value with y of 0 is equal to pi over 4. Okay, so let's see here. So first thing we do in general is if they give us a y prime, we would prefer the other notation, Leibniz notation, which is dy dx is equal to x e to the x cosine squared y. From there, we can try to separate. Let's move all the y's with the dy and all the x's with the dx. So this is going to become dy all over cosine squared y is equal to x e to the x dx. Okay. Now you guys know after doing the previous video that you can now integrate both sides. This is how we're going to solve. Oh yeah, so they might say something like solve initial Okay, so let's see here. We know that this is actually secant squared y dy, right? That's what cosine squared in the denominator actually is it is actually secant squared. Now this one is going to be a flashback to chapter 7 when we were doing ultraviolet voodoo, or the mathematical term is integration by parts. Thank you, Dr. Hughes, for calling it ultraviolet voodoo. That's a good way to remember it. So now we know that the integral of secant squared y is actually what? Well, isn't it just tan y? So we know that that is actually just plain old tan y. However, this guy right here, we're going to have to do integration by parts. So we're going to need to build a u du and a v dv. Always remember your limit. Right, logs, inverse trig, polynomials, exponentials, and regular trig functions. Right. So this is kind of the way we decide. It works most of the time. It's not perfect, but it works most of the time. So we are going to let our u be our polynomial. So this is x, and then the derivative of x would be dx. And then we're going to let dv be e to the x. Remember, you have to name your dv and your u. Our dv is e to the x. Well, the integral of that would be v, and the integral of e to the x is just e to the x. So now we're going to write our integration by parts. So we know that it's u times v, or ultraviolet. That's our ultraviolet voodoo. So u times v is x e to the x minus the integral of v du. So v, which is e to the x, and du, which is dx. So then we're going to have tan of y is equal to x e to the x minus e to the x plus c. Okay, is everybody okay with that, hopefully? So now we can move on. Now we can say that if we want to find c, we remember that y of 0 is equal to pi fourths. So that means that tan pi fourths equal, and then we plug 0 in everywhere else. So this would be 0 e to the 0 minus e to the 0 plus c. We plug everywhere else for x. So we know that tan of pi force is 1, and this is equal to what? Negative 1 plus c. So then c will equal 2 once we solve that. Okay, so we now know c. So now we can come over here and write our tan y is equal to x e to the x minus e to the x plus 2. But now we can take the arctan of both sides, or tan inverse. So we have tan inverse of tan y is just y, and this would become tan inverse of x e to the x minus e to the x plus 2. And that would be our solution to the differential equation. And again, that means when we plug in this value for y, we would get an identity on both sides. Okay, so that was the next problem we're going to do, and you're going to start seeing that with the harder problems. You're going to start seeing, you know, combinations of other integration techniques. Let's try one more of these initial value problems, or we actually have a few more that we're going to do. Let's see here. So I have this one. I have y prime is equal to 2x plus 1 divided by y plus 2. So once again, we know the first thing we're going to do is we're going to convert this to dy dx equals 2x plus 1 divided by y plus 2. And now we're going to rearrange this, and this is going to be y plus 2 dy equal to 2x plus 1 dx. Now they gave us an initial condition for this. They said solve with y of 0 equals 2. And it says do not solve. So a lot of times it's just too difficult, or it just can't be done. Okay, so we're going to move forward with that. So we now are going to integrate both sides. So this should allow us to end up with y squared plus 2y, and this will be over 2, equals 2x squared over 2 plus x plus c, right? So let's do a little cleanup on this. So this will be y squared over 2 plus 2y is equal to x squared plus x plus c. Now we know that y of 0 is equal to 2. So that means that our y's are going to be worth 2 and our x's are going to be worth 0. Okay. So let's plug this in. So this would be 4 over 2 plus 2 times 2 is equal to 0 squared plus 0 plus c. So this would be 2 plus 4 is equal to c. So 6 is equal to c. We have our c. So then that means we have y squared over 2 plus 2y is equal to x squared plus x plus 6, I believe. Yeah, and that's why they don't want you to try to solve for y, because it would be kind of or impossible or very, very difficult. So this would be our solution to the differential equation. Let's look at another one. So I believe there's a pretty bad one around here somewhere. Let's try this one. I guess this one's not too bad. So we're going to work with solve y prime equals 2x square root of 1 minus y squared. I do want you to solve okay. So what we're going to do is we're going to do dy dx equals 2x square root of 1 minus y squared. We're going to separate it, or see if we can separate it. Let's see, this would be dy over square root of 1 minus y squared. You divide both sides and by the square root of 1 minus y squared. And then you can have 2x times dx. So this isn't such a bad one. Now it would get worse if we did not have the formula memorized for this guy right here. Remember, there's supposed to be a formula for this particular one. When it's the square root of 1 minus x squared, we called it arc sine of x. So this is just 1 minus y squared, so it's arc sine of y. So we're going to go through with this and say, well, this is sine or arc sine of y is equal to 2x squared over 2 plus c. Now we know that we have to take the sine of both sides. So this would be y equals the sine x squared plus c. And we're good. That's it. So that's the solution to our differential equation once again. So not so bad. Let's do another one over here. So let me see how bad this one is. Yeah, I guess it's not so bad. Let's try something with an e, with an exponential. So we have e to the y, and we're going to do the same thing. We're going to solve. You know what? Let me write it out. Solve. If I go to print this as a PDF, it might be beneficial. I try to keep everything as almost one page in size. So let's go with this one. Solve. Equals 3x squared over 1 plus y. We're going to give initial condition on this one. Y of 2 is equal to 0. So let's see here. This is going to be e to the y dy dx is equal to 3x squared over 1 plus y. So then what I'm going to do is, e to the y times 1 plus y dy is equal to 3x squared dx. So I separated it. I got it written in the form that I wanted. Now I'm going to really quickly distribute this. So this will be e to the y plus e to the, e to the y equals 3x squared dx. So now what I'm going to do is I'm going to integrate both sides, but I'm actually going to split this integral as two separate integrals. So this will be the integral of e to the y dy plus the integral of e to the y dy is equal to, I guess we can do this one in our head. This will be 3x cubed over 3 plus c. And let's clean up this left-hand side now. Okay, so this left-hand side, we already know this guy is going to be e to the y. However, this one's going to require integration by parts again, just like we did in the last problem. So we're going to say u is equal to y, du, or not the last problem, but one of the previous ones. Du is equal to dy, v is equal to ey, and dv is equal to ey. So when you integrate dv, which is e to the y, you're going to get e to the y again. So this is going to be, this is the, I'll leave this in green so you see that this is the ultraviolet voodoo, or the uv minus the integral of v du. So u times v would be y e to the y. Wait a minute, this is a plus sign. Sorry about that. Minus the integral of, let's see here, minus the integral of v du. So that would be e to the y dy. And then we know that this equals x cubed plus c. So now we have e to the y plus y e to the y minus e to the y is equal to x cubed plus c. Now here's the thing, we have a little bit of cleanup to do. This and this combine and become 0. So what we're really left with is y e to the y equals x cubed plus c. Now our initial condition says y of 2 is equal to 0. So when we plug 2 in, we should get 0. So that means 0 is equal to 2 cubed plus c. You could fiddle with that e to the y and get it to work, but in general, this is what we're going to get. So then we're going to have c is equal to -8. Okay, so we now can write our answer. Bring it back up over here. So our answer will be e to the y is equal to x cubed minus 8. Right? So this would be our solution. All right. So hopefully you guys are okay with this solution to the differential equation. I have another one I'd like to look at. So if we're, now you guys understand that each one of these is basically just showing you different ways you can separate differential equations, but this only works if the differential equation is separable. So remember, why does it feel like all of these are separable? Well, because that's the only method we kind of have currently to work with is separable differential equations. So there's other differential equations out there that don't work with separation. So you have to try something else. We're going to learn linear differential equations at the end. But I just wanted to let you guys know why it seems like all of these are working. It's because they're supposed to, okay? And again, you should kind of like differential equations. It should feel very, this part of differential equations in terms of separable should feel very concrete. So let me try one last one, and then this will be the end of chapter 9.3. So we have y prime is equal to x minus 1, oops, plus xy minus y. Okay, so let's do our normal thing. dy dx is equal to x minus 1 plus xy minus y. Now, you might want to try to pause the video real quick and see if you can do a separable differential equation on this. You might run into some hiccups. So pause the video and see if you can separate this. Okay, hopefully you actually listened and paused it and tried to separate it. If not, you're just hearing me talk to myself. So the thing is this problem, if you try to separate it by normal means that we've been doing the previous ones, it just doesn't quite work right. You can't get all the dy's with the y's, and you can't get all the dx's with just the x's. So we got to try something else. So what I'm going to do is I'm going to kind of look at this guy, and I'm going to look at this guy. So these two terms and these two terms. And I remember that when you have 4 terms, you can try factor by grouping. So I'm going to try grouping. Now they both have a y in common, and that's going to leave me with an x minus 1. Now I'm going to bring that over here. You know what? I'll put that in red. So that actually means that now I have dy dx equals, they both have an x minus 1 in common. So I'm going to factor out an x minus 1, and that's going to leave behind a 1 plus y. So now I can separate. So now I can separate and divide both sides by 1 plus y. So this will become dy over 1 plus y. And this will become x minus 1 times dx. So now this becomes much easier, or a much easier integral. We integrate this and we integrate this. And this now becomes the natural log of the absolute value of 1 plus y. And that is equal to x squared, x squared over 2 minus x plus c. Okay, now some people might stop here, but you can actually solve for y in this problem. We're going to use a property of exponents and logs and exponential functions. Oops, let me do it in a different color. You can rewrite this like this. And what that would do is that would allow us to do 1 plus y. In general, when you use the property of e to the natural log of something with absolute values, it becomes the positive. Okay, so we're going to have e to the x squared over 2 minus x plus c. Now there's one little extra thing that your book will ask you to do, and it's to clean this up even better in terms of constants. So this is x squared over 2 minus x times e to the c. So what I did is I said, well, this is technically e to this, and e to this all being multiplied. But when you know that when you're adding and when you're adding exponents, you actually were multiplying the bases. So this allows me to have this guy right here as a constant. But what's e? It's a constant. What's c? Some constant. So what's e to the c? Some new constant. Let's call it d. Oops. Let's call it d. So now I have 1 plus y is equal to e to the x squared over 2 minus x times d. And I am just going to subtract the 1 over. So we have y equals d e to the x squared over 2 minus x minus 1. And this will be our solution to our differential equation solved for y. Okay. And this is our new constant that we developed by e to the c. I believe they may. So I think that's going to be it for chapter 9.3, you guys. Let me know if you have any trouble with the homework and we can talk about it. But that'll be the end of this video. Take care.